So hey guys, my name is Zara and I'm a PhD student over at Monash University. Today I'll be talking to you about the production of aluminium-26 in low and intermediate mass binary systems. The origin of the elements is a fascinating topic as it tries to answer one of humanity's oldest questions, and that is, where do we come from? Hopefully everyone in this room knows that everything heavier than lithium was forged in one way or another by a star. Most of you are probably familiar with this plot from Kobayashi, and this plot shows us the elemental abundances of all the elements of the periodic table as a function of time. And it also gives us a glimpse of the origin of these elements. The element I'm focusing on today is aluminium-26. So aluminium-26 is a radioactive isotope with a half-life of about 700,000 years. Now, it is an important isotope as its radioactive decay acts as a heat source for the planetesimals of early solar systems. However, there is some mystery surrounding the origin of aluminium-26, and that is that there is a mismatch between the abundances which we observe compared to the abundances that we predict from stellar models. So what could be happening here? The majority of galactic aluminium is thought to have originated from massive star. However, today I'll be talking about asymptotic giant branch stars, or AGB stars for short. AGB stars are dying low mass stars of up to low or intermediate mass stars of up to 8 solar masses. They're in their final nuclear burning phase before they transition off into white dwarfs, and they are thought to have made roughly 3 to 4 solar masses of the aluminium-26 that are within our galaxy. So how do these stars make aluminium-26? Towards the end of the AGB phase, these stars begin to experience what are known as thermal pulses that are driven by unstable shell helium burning, and this is characterized by the thermal pulse cycle. I have here a diagram that's just showing a slice of the stellar interior of an AGB star, and we are going to follow aluminium-26 on the journey from the point where it is made within the star to the point where it gets ejected to enrich the space surrounding it. Aluminium-26 is made within the hydrogen burning regions of stars. During the interpulse phase of the thermal pulse cycle, the hydrogen burning shell is making aluminium-26 and depositing it into the intershell region. Now, the thing with low and intermediate mass stars is that they do not explode. Instead, they slowly eject their envelopes by stellar winds. So if any of this aluminium-26 is going to be ejected, it needs to be transported up to the surface of the star. And the way that AGB stars do this is through a mechanism known as the third dredge-up. Now, the third dredge-up describes the expansion of the convective envelopes into regions where it was once previously nuclear burning. So the third dredge-up will actually penetrate into the intershell and scoop up the aluminium-26 to transport it up to the surface. However, the catch here is that the aluminium needs to survive up until the third dredge-up. So after spending some time on the interpulse, the helium burning shell ignites, and this begins the thermal pulse phase. One of the products of the helium burning shell are these lone neutrons, which moves into the intershell and then gets mixed up with the aluminium-26. Now, aluminium-26 loves to fuse with neutrons. And as a result, the majority of the aluminium-26 that's made by the hydrogen burning shell actually gets destroyed in the very next thermal pulse. And by the time we cycle around to the third dredge-up, there's only a very small amount of aluminium-26 left to be mixed up to the envelope. The story is a little different in stars that are greater than about 5 solar mass. These stars are so massive that the bottom of their convective envelopes are hot enough to sustain hydrogen burning, and this is known as hot bottom burning. One of the benefits of hot bottom burning is that since this occurs within the envelope itself, any aluminium is almost immediately brought up to the surface. There are also no free neutrons around to destroy it. So this means that hot bottom burning is responsible for making the majority of the aluminium-26 that comes from AGB stars. So what is the problem here? Well, the problem is that most galactic chemical evolution models, including the one that's used to make this plot, base their calculations on models from single AGB stars. However, it is observed that 50 to 75% of low and intermediate mass stars have at least one stellar companion in what is known as a binary system. What happens when we have a binary system? So binary systems have this thing called the Roche lobe, where within the Roche lobe, mass is gravitationally bound to the enclosed star. However, should a star expand beyond its Roche lobe, mass begins to transfer from one star to the other, and this is known as Roche lobe overflow. So stars with deep convective envelopes, like stars like AGB stars, for example, they do not shrink back within their Roche lobes once they overflow. And as a consequence, their envelopes are almost entirely stripped off and transferred over to the companion star. Now you can imagine that this would wreak all sorts of havoc on the stellar evolution of the star. In addition, the companion star may also overflow its Roche lobe. So when we have two stars both overflowing their Roche lobes, we have what's known as a common envelope system, which may force our stars to merge. Now, a general rule of thumb here is that the closer the stars are to one another, the more likely they are to interact. However, wide binaries are not necessarily safe from mass transfer either. As AGB stars have thick stellar winds, these stellar winds may get caught within the Roche lobe and transferred over to the companion star, and this is known as wind Roche lobe overflow. So how does this affect aluminium-26? To try to answer this question, we look to binary population synthesis code binary C, and we evolve a grid of stars with an initial mass between 0.95 and 8.5 solar masses. And we do this at solar metallicity. And from our models, we are able to calculate the stellar yields produced by our binary systems. Now, the stellar yields are defined as the mass of the total mass of a nuclei that's ejected by the star over its lifetime. So just a caveat, we are only considering the stellar yields ejected by stellar winds, and we are ignoring the contribution from novae and supernovae. I have a little animation here on the right that just shows us the aluminium-26 yields for the binary stars in our grid, and we can see that at a glance, there are some regions that are showing up in bright yellow that telling us that there are some binary systems that are producing a very large amount of aluminium-26. Please transition. Okay. So how does this look from a stellar population? So I have here a plot showing us the stellar yields produced by a lone intermediate mass stellar population as a function of the initial mass of the stars. Now, the binary fraction describes the fraction of stars within our population that are binary. So right now it is 0. So this means we are currently looking at the stellar yields produced by a single star population. However, if we were to increase this binary fraction, how would this plot change? So doing just that and bumping up our binary fraction to 0.75, meaning that every three out of 4 stellar systems are binary, we find that at a glance that this population produces 25% more aluminium-26 than our population of only single stars. Now, zooming in on this plot, the colored yellow portion here is the contribution made by the single star contribution. The dark blue is the aluminium-26 that's provided by the binary primary stars. So the primary star is the more massive star in the pair, and the light blue comes from our secondary star, so the initially smaller star in the pair. Yeah, so just at a glance, we can see that it's the secondary stars that's putting in most of the work here. And we found that it's wind Roche lobe overflow onto more evolved secondary stars, and this allows those stars to endure much longer hot bottom burning at much higher temperatures, which means more aluminium. We also find that binary evolution can help out low mass stars as mergers that would allow stars that initially have too light for hot bottom burning to actually trigger hot bottom burning. We also have this region where we actually have an underproduction of aluminium-26. And what's happening here is that binary evolution also causes some of our stars to explode. And that just cuts them out of the calculation. But the main takeaway here is that binary evolution does allow some of our stars to have much longer and hotter hot bottom burning than they normally would if they were single stars, which means we have more aluminium-26 being made. So I'll just have a quick summary before I let you all go. So we are investigating how binary evolution can influence the aluminium-26 production of low and intermediate mass stars, and we use binary C to simulate a stellar population at solar metallicity. And in our population with a binary fraction of 0.75, we find that this population produces roughly 25% more aluminium-26 than our population of only single stars. And this is mostly due to mergers and wind Roche lobe overflow, allowing stars to have longer and hotter hot bottom burning. If you guys are interested in the more gory details, we do have a paper that will hopefully be submitted very soon, and you're also welcome to come up to me and have a chat. Anyway, I thank you all for sticking out this long. I was expecting this room to be much emptier. So that's all from me, guys. Thank you very much.